Good evening and welcome everybody. It's Obi-Wan Pez for N Simplex Pachinko. We are going to be doing some more cracking the GRE math subject test. Second edition from Princeton Review, copyright 2002. Good news is that the math, generally speaking, doesn't change. And the curriculum certainly hasn't. So essentially, we're looking at the same sort of stuff that we did back in 2002, now in 2026. So, good times. If anybody does have any particular questions on other math subjects, math topics, individual lessons, individual concepts, whatever you have, let me know, and I will get to all of that. Those of you who are joining us on YouTube, hi, how you doing? You'll notice a distinct lack of music for the near future, possibly forever. We'll see how it goes. Despite being called No Copyright Sounds, the company has become under scrutiny or something for having copyright claims against that. I don't understand how that's even possible, given the agreements that would have had to have been signed to be on a channel called No Copyright Sounds. So, I'm going to try to make sure to to remember to turn on the audio whenever I'm playing a game. So we'll see how it goes. Unfortunately, the OBS channel selection stuff doesn't really work terribly well when you're doing when I was doing like select this particular video game, it would still do the exact same issue that I've got with the window select. So I don't know how to fix it. So for now, we're just gonna do this sort of wild and crazy sort of thing and hope that I don't mess it up too bad. So actually, come to think of it, right? I should get a post-it note or something. I'm sure I have some around. Write a little note to myself to remind. At any rate, how are y'all doing? Hope you are having a great first half of your week. Good, that still works. Yeah, hope you're having a good first half of your week, and things are going pretty well over at the Obi house. Alright, we're going to just shove that right on the corner and say check audio for OBS channels. Right out. So, tonight we're going to be working on Taylor series. So we were just talking about power series and how when you have a power series very generically, this is going to be, I prefer K. It doesn't really matter all that much. We're going to start with K equals 0 and go off to infinity. And then we're going to take a sub K and multiply that by, okay. And multiply that by x to the k. And what that's going to do is allow us to have a sub 0 times x to the 0, but naturally we just don't want to write that. A sub 1x plus a sub 2x squared plus all the way out to a sub n x to the n, and then that is going to continue going on forever and ever. So, that's interesting. I have too wide of a window, I think. Something more like that. How we doing? Not even. Okay, interesting. Sorry, the resolution on this also got... Oh, no, wait. I think this was from the other day when I moved it. I had to move it on my screen because something was off the side. Yeah, there we go. All right, if we go like that-ish, should mostly be okay. Just gotta make sure not to put myself in the bottom corner. And then we can go over that far. Cool. Margins. Okay. All right. So, when we look at power series, this is what we're going to be looking at. On the other hand, if we want to talk about the Taylor series, this is a particular version of a power series that had been created by Brooke Taylor from England way back in the I want to say it was like 1650 or something like that. Let's just look it up real fast because that's a thing we can do. Uh, 1685 to 1731. So it would be amazing if he did it in the 1600s. So his papers on what are now known as the Taylor series, direct and indirect methods of incrementation, 1715 is probably his best introduction to that particular thing. Taylor was elected as a Fellow of the Royal Society in 1712. So, 27 years old. And in the same year, Taylor sat on the committee for adjudicating the claims of Sir Isaac Newton and Gottfried Wilhelm Leibniz, acting as secretary of the society from 1714 to 1718. Oh, of course. From 1715 onward, Taylor's studies took a philosophical and religious bent. Of course they did. That's weird. Okay. Da, da, da. Well, that's just depressing. Taylor married Miss Bridges of Wallington, Surrey in 1721 without his father's approval, leading to his estrangement with his father, which improved in 1723 after Taylor's wife died in childbirth, giving birth to a son. The son did not survive either. In 1725, he married with his father's approval Sabetta Sawbridge of Ullaty, Kent. She died in childbirth in 1730, though his only daughter Elizabeth survived. Taylor's father died in 1729, and he himself died 2 years later at the age of 46 in Somerset House, London. Oi. Yeah. Life was not kind to people back then. I mean, not that it's great now, but it certainly has been improving over the long span of human history. Let's see. Cool. Okay, so the Taylor series is a particular set of power series, right, such that A sub k follows a very particular rule. So, what we want, right? So here's what Taylor really saw as a goal. Right? We want the power series to have the same function value as our original function f of x at some particular non-singular point, x sub 0. So a lot of times, this is also done much more easily with when x sub 0 equals 0, we have what's called the Maclaurin series. This is just a matter of giving credit where credit is due. So Maclaurin was a Scottish mathematician. Colin Maclaurin, who made extensive use of this special case of Taylor series in the 18th century. So, roughly speaking, in the same time where Brooke Taylor was alive, but yeah. So he was born in 1698 and died in 1746, age 48. Both of them burned that candle very quickly. And Maclaurin was a mathematics professor at the University of Edinburgh at the age of 27, upon the recommendation of Isaac Newton. Nice. Newton was so impressed with Maclaurin that he offered to pay the salary himself. Interesting. Oh, and that's right. We did go see Colin Maclaurin Road in Edinburgh. So when we went to Edinburgh this last spring, I think, we went to Greyfriars Kirkyard in Edinburgh and saw the plaque up, stone carving up on the wall of Greyfriars that had, it says right here, infracitus est Colin Maclaurin, Mathis olim in Eden prof. Yeah, in Academy Edinburgh professor, electus ipso nutano suadente. So I don't speak Latin, obviously. But essentially it's his tombstone that just reads like, here interred, or in memorial of Colin Maclaurin. So it was kind of cool that, like, I was like, hey, I know that guy. My kids are like, what are you talking about? Okay. So we want the power series to have the same function value as our function f of x at some particular non-singular point x sub 0. So this says that a sub 0 should be equal to f of x sub 0. Yes, right. Yes. So the only way that we can really make that work well is if we say, I've got an idea. Let's make the first term, right, a sub 0 times parentheses. This is our x term raised to the 0 power. Obviously, that's not going to matter what we do with this. It's still going to be just x and then raised to the 0 power, no matter what else is in there. However, we need all the rest of these terms to then end up not existing. So we need all of these other terms to go to 0 when we plug in x sub 0 into the entire thing. So here we say, well, let's shift this over to this particular point, right? Take everything, shift it to the right to x sub 0. I grant you, right, it might be to the left. That's okay. But most of the time, it ends up being to the right. So we say here, well, this is 0 to the 0, but realistically, like, before we even get here, we use the 0 for the exponent, and we just say, okay, this is just a0. Right, so if f of x can be equal to an infinite series, then f of x sub 0 is going to be equal to a sub 0 plus a sub 1 times x0 minus x0 plus ... So again, these terms are all going to go to 0 from this point on. And the only thing that's left is now our first term. Right? So the function value at x sub 0 and the series value at x sub 0 are identical to each other. Okay, so that's step one, is to establish that we can make that happen. Yeah. All right, then number 2, step 2, we want all successive derivatives to have the same property. So if we want all successive derivatives to have the same property, then we're going to say, okay, this is going to be a sub 0, right? F of x is going to be equal to a sub 0, yeah, we're not even going to bother with x to the 0, plus a sub 1 x plus a sub 2 x squared plus a sub 3 x cubed plus dot 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 all the way out to a sub n x to the n, and then continue ad infinitum. So keep going forever. Then, right, sorry, we're going to make this not just x. Damn. We're going to make this parentheses x minus x0 plus a2 parentheses x minus x0 squared plus dot 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 plus a sub n times x minus x0 to the n plus dot dot dot. Right? Keep going forever. So this is our new power series that we're using. It is a shifted power series, but nonetheless, it is a power series. Then we want to say, okay, so f prime at x should then be, well, a sub 0 is just a constant, so now it's 0. Plus x, a sub 1 is now going to be in this position. We now have our power series is going to look at taking the derivative of the power. So we take the power, which is 1, it comes down front and gets subtracted by 1. So now we've got 1 x minus x0 to the 0. Well, that's gone then. Right? So x minus x0 to the 0 is now gone. And then we've got plus the 2 from the square term is going to come down, make it 2a2 parentheses x minus x0 to the first power now, plus dot dot dot, continue on, n times a to the n, no, a sub n, sorry, times x minus x0 raised to the n minus 1 plus dot dot dot. All right, what about f double prime? Well, we do the same thing here. A sub 1 is now a constant, so it goes away. And then we're left with 2a2 times, now we take the derivative of the next x term, which again has an exponent of 1. It now becomes an exponent of 0, so that one is gone as well. All right, so then plus, and then this is going to be, if we think about what's happening on the next term, right, our cube term, then what we've got is the cube term dropped its 3 on the first derivative, and then it's going to drop the 2 on the second derivative. So this is now going to be 2 times 3 times a sub 3 times x minus x0 to the first power, plus the next one's going to be a 3 times 4 a to sub 4 x minus x0 squared plus dot dot dot. We're going to end up with n minus 1 times n times a sub n times x minus x0 to the n minus 2. And then that's going to continue on forever. And again, we can assume that this pattern is going to hold as long as we want to. You can actually work it out step by step, individual term by individual term. Go ahead and work it out. Right? But the point really is that what's going to happen is we end up with fk of x. Right? So now we want to take the kth derivative. So, if we do this just generally speaking, right? This is going to mean that the first k minus 1 terms have all become constant and have now been knocked out. So the first term that's going, oops, that's not what I wanted. The first term that's going to be present, if we look at all of the previous ones, well, with the 0th derivative, we had a sub 0. First derivative, we had a sub 1. Second derivative, we had a sub 2. So with the kth derivative, we have now a sub k as our first term. And now we've also got, sitting out front, did I? I did. Nah, it's fine. Right now, sitting in front, this is going to be a little bit weirder. It is a lot weirder. That'll be all right. So we're going to get k factorial out front times a sub k times, well, the first term is just going to be that. Plus, the second term is going to be k plus 1 factorial over 1 factorial. So technically you can make this over 0 factorial. The number of terms that you have to clear off the front of it. Here we have not dropped the 1 yet, so you wouldn't see it necessarily. Here we have not dropped the 1 or the 2 off of the square term. Right, so this is now x minus x0 raised to the first plus, this is going to be k plus 2 factorial over 2 factorial times x minus x0 to the second plus dot dot dot. However far that's going to go. Now what we can do here is we say, you know what, let's do kth derivative of x sub 0, or evaluated at k sub 0. This is now going to take all that stuff that still has x minus x0 terms, and guess what? These are all zeros. Every single one of them is now 0. So what we're left with is really just this first term. That's it. So we've got a k factorial times a sub k. Which then means a sub k, the individual term that we're looking at, the individual coefficient that we're looking at in the Taylor series is going to be the kth derivative at x sub 0 over k factorial. So if you were ever wondering, like, where did this thing come from? That's it. Right? So one more time, how do we get this? So we started out from the premise that the Taylor series said we want the value of the function to be the same as the value of the function to be the same as the value of the power series at a particular point. We'll call it x sub 0 to be generic. When we do that, we find that all we have to do is worry about the constant term. What is the constant coefficient? Well, it's the same as the function value at that same point. Cool. Then, every time that we want to say, okay, well, not only should the function value be the same, but like the derivative should be the same. So, whatever our function has as a derivative at that point should also be the same as the derivative of our power series. Should have the same stuff for the value of the power series. And then we do that, we take the first derivative, and again, evaluate it at x sub 0, all those terms go away. So we're just left with 2a sub 2, just 2a sub 2. Nope, I'm wrong. Sorry. All those terms are cleared. The only thing you're left with, if you want the derivative to be the same at x sub 0, is just a1. Right? A1 should be equal to just the derivative evaluated at that particular point. It's when we start getting into the next things, right? So these also have had exponents become coefficients. So now it's messing with things. So now we say, well, if we want the same curvature, the second derivative, in the function as with the value of the power series at that point. So now we have to think, okay, well, if we plug in x sub 0 again, all the higher terms go away, and now we're just left with 2a sub 2 is equal to the second derivative of f at x sub 0. So a sub 2 is going to be equal to half of the double derivative of f at x sub 0. And then we generalize. So again, all these terms, all the rest of these terms here are all going to go to 0, so they don't count in terms of the Taylor series, trying to find out what the coefficients are going to be. If you tried to say, well, what if I don't set it to be x equals x sub 0? What if I just, leave it as like a generic Taylor series? And like, sure, but there's a problem with that. Or general power series, right? There is a problem with that in that you don't necessarily have guidance on what form your particular terms should take. Again, Taylor series is very nice because we go through this and we say, all right, look, the point should be at the same point. The slope should have the same slope. The curvature should have the same curvature. It might not be exactly the same, and it might only be the same at that one point. But that's really what we're going for. Right? And then all further derivatives, your, jerk, snap, crackle, pop, all that stuff should all be the same value for the function and for the power series. So when we do that and we rearrange so that we get the coefficients as a function of our function f and its derivatives k, then we end up getting this stuff. Right? So, such that a sub k is equal to that stuff. The kth derivative of f located at x sub 0 divided by k factorial. Right, so we have a function f of x that I'm going to be one of those guys, which we are attempting to model with a power series. Right, so for standard power series, we're just making this infinite series, which then, right, f of x will be equal to this infinite series. As long as it is truly k equals 0 to infinity, then the power series will match the original function f of x exactly. Once you start saying, like, well, I don't have a theoretically infinite amount of time to model this thing. I only have a certain number of days. I only have one lifetime. Then we look at this and say, okay, so we don't need to do all of them. How far can we go and get a reasonable approximation? So there are a number of different things that we could do here. If we wanted, like, a value of pi, for example, I don't recommend it, but if you wanted a value for pi, you could, in theory, work out what the inverse cosine of -1, yeah, what the inverse cosine of -1 is going to get us. So that'll get you pi. And it'll get you an ever-increasingly accurate value for pi the more terms you add in. I would say that the issue with that particular example, is going to be that we don't have, like, super accurate values of the no, I take that back. What we don't have is a nice derivative of the inverse cosine formula. Like, you could do it. It's just going to get annoying real quick, because now you've got all these square roots in it, and fractions, I believe. That one's an interesting one. The example just says, like, find the power series approximation for the following, or power series equivalent. And they just give me two functions, which is fine. Uh, all right, so the derivatives of our inverse cosine, if we wanted to actually get a value for, again, pi, we would need -1. And that is not going to work for us because that ends up going vertical. Right, so that is a singular point. We could instead go for, is there another nice value that... I mean, might be better off with an inverse tangent. um, I think this is probably a little bit advanced. Oops. Taylor. Now this also allows you to do multiple things. If this was just the question, right? Assessing which function you would want to use is actually a thing. So for this, we do have that the inverse tangent of 1 is going to be pi over 4. So this would be 4 times the inverse tangent of 1 is going to be equal to pi. So if we wanted to use a Taylor series for this, then what I'm going to do is say, okay, let's do a Taylor series with this particular function right here. We'll find a general formula for it first, and then we'll also like do a bunch of terms and see how it comes out. Right, so if we don't know what the decimal equivalent of pi over 4 is, or again, we're trying to find the value of pi using some sort of infinite series, right? This is one option. It is not the most efficient by any means. I believe that record goes to Srinivasa Ramanujan, who did an insane series for pi, which involves a rational number that I can't even remember. Like it's a 5-digit number divided by a 5-digit number times some things that are factorial, and it gets crazy. And like even in the modern era, there aren't many formulas that do it as well as succinctly as the Ramanujan formula. It's just, it kind of hurts my feelings that he was able to just like literally divine this particular formula. He credits it. He credits it. There we go. To his house god. So in Hinduism, Each individual adherent and their house usually have a particular god that watches over them. I can't remember. Goddess. Namagiri. Yeah. Namagiri Thayar, the Hindu goddess. Within the Namakkal district of Tamil Nadu. Nope. Okay, sorry. Namakkal is the is the municipality. I'm sorry, that was the disambiguation page. All right, Namagiri Thayar is the Hindu goddess form of Lakshmi. Let's see. Lakshmi, consort of Vishnu, was angry and performing penance because Narasimha Vishnu had assumed the avatar of Narasimha, did not forgive the Asura king whom he killed. Goodness. Hanuman was carrying the Shaligrama image and requested the disguised Lakshmi to hold it until he returned. Lakshmi could not bear the weight and placed the image at this place of the temple, which grew into a mount before Hanuman could return. Narasimha appeared before both of them and set his abode at this place in the stone statue. The place where Lakshmi got back into the chest of Vishnu and can be seen even today in the main deity's chest. Alrighty. Cool. Small history of religion lesson. It really is not what I clicked. What did I... Why did you redirect me? That is not what I clicked. What? I really don't understand. Namagiri underscore Thayar. No, I want those words right there. It's just taking me to the Narasimha Swami temple in Namakkal. Okay, whatever. Lakshmi. Hmm. Yeah. Incarnation. Namagiri Thera. Theyar. Consort of Narasimha, fourth avatar of Vishnu. Alright. I don't know when that is supposed to be. Yeah. At any rate. So yeah. Uh, Ramanujan felt one night inspired because Namagiri came to him and inspired him to like write down a particular formula and would just like expound on details of the stuff like that. And Ramanujan hadn't had any like formal mathematical training. He had just basically he was a motorcycle repairman who was learning math in his spare time and did exceptionally well. In addition to having just intuition beyond what anybody could even think of, like could even imagine. Um, so he ended up doing really well with that. He sent letters and letters to. I'm getting off topic. It's fine. Sent letters and letters to Oxford and Cambridge and anybody who would listen, and like all of them were the old white boys club of somebody from the colonies is trying to learn mathematics. So cute. And then G.H. Hardy, the same G.H. Hardy of this book I have over here somewhere. I feel like it is still on the shelf and not randomly stacked, but you never know. Yeah, that's Osgood and Drystein. It is an analysis book, so it should be back here. That is not true. Okay. Tensor calculus, yeah, partial differential equations. Boo. I can't find the right one, but it's fine. It's the one that has the cover falling off. A Course of Pure Mathematics, G.H. Hardy. Yep, there we go. So. Fifth edition, Cambridge University Press, 1928. So, this particular one was donated to me by an old University of Maryland professor who had retired many years hence, and his son was cleaning out his attic and was like, "My God, there are a lot of math books here. Hey, Obi, do you want these?" And I'm like, "I mean, I can go through them." I think I told you guys I found a copy of a book by John von Neumann. I don't remember which one it was. I could probably find it. Evaluated like the perfect copies of it that were going for sale on like Abe books or whatever it was, were going for $750. And I was like, oh. I'm like, I don't feel comfortable having this in my house. Anything that valuable. It's like I don't want to be I don't want to be in charge of this. So I called them up and I was like, look, as far as I'm concerned, this is still yours. And he was like, I'm going to put it on my shelf because he's been a computer scientist slash engineer slash whatever for many years and worked at Johns Hopkins Applied Physics Lab and was like, I think it would be a great conversation starter. And I'm like, absolutely, 100% yours. Please take it away. I was like, I can go through and I can, sell it for you if you want, but I am definitely at least getting you a massive cut of this. He was like, no, I think I'd rather keep it. I'm like, great, yours. Right. So if we assume that f of x is going to be, we could do 4 inverse tan of x, or we could just do inverse tangent of x. I'm not going to be too precious about this. 4 is fine by me. So we're going to go f prime is going to be 4 divided by 1 plus x squared. F double prime, this is where it starts getting a bit fun. So here, we're going to have, this is 1 over something. So now this is going to be a negative 1. This now is on the bottom as 1 plus x squared, because now our exponent went from a negative 1 to a negative 2, and then we have to do the chain rule, by which we end up getting a 2x here. If we do a third derivative, this is where it starts becoming a pain in the rear. So, we have to do this as a product rule, or quotient if you prefer, but either way. Right, so this is a negative 8x divided by parentheses 1 plus x squared all squared. If we take the derivative again, this is going to be the derivative of the top times the stuff in the bottom times the fraction, which includes the stuff in the bottom. So we're going to get a negative 8 over parentheses 1 plus x squared parentheses squared. Then, let's get rid of that. It's fine. Then we have to take the sum of that and what happens when we just take the top, leave it as it is, then take the derivative of the bottom again. So here this becomes now a negative 2 times that, parentheses 1 plus x squared, parentheses to the third, and then we multiply by the derivative of the inside, which is again 2x. So this gets really complicated really quickly. This is going to be a negative 8, and if we make this 1 plus x squared, we can now make this all one fraction with 1 plus x squared parentheses cubed on the bottom. And then over on the other side, we now have a plus 1632x squared. Righto. So, ad break's going to start. We're going to go for 3 minutes, and then we'll come back, do a little bit of Tai Chi, show you what I learned today. So, see you in 3 minutes. Thanks for coming. Well, hello there, everybody. For anybody who's new, my name is Obi-Wan Pez. This is Simplex Pachinko, and we are going to be doing some more cracking the GRE after this little fitness break. So, we're going to do a little bit of Tai Chi. I learned some more stuff today, so we'll be continuing the, as he called it, the first third of the form. He showed me the rest of the first third, and it appears to be about like 6 individual moves away. So we're getting actually pretty close. All right, a little bit of warm up first. So swinging side to side like this, and let gravity kind of take your arms, and then we're gonna kind of push out of our what's called the inguinal crease. It's that place between your thighs and your abdomen that like your groin muscles are. So we just kind of tuck into it as we go toward one particular side, and then push out of it, and it causes our hands to get a nice little whip action. This increases the blood flow to your hands. It also helps to get your elbow and shoulder joints worked up a little bit. And we do the same here. Just real small movements on the knees. Going to allow the hands to, again, just kind of go flying on their own, as if you were a child on a swing set trying to pump to go higher. Right? Gives you a little bit of a push every time you do it. Hey, Afru, how's it going? Welcome back. Right, and then we also we'll do just a couple of these. So we're gonna lean back, reach, and then come back, steeple the fingers, and come down. Do a little bit of a squat. Come back, and down, back, down, down. Ideally, you want to do like 10 or 20 of each of these things, but you know, who's got time for that today? So, again, same kind of movement here. Step forward and backward gently, and cause that shift in your weight to kind of whip your arms back and forth a bit. Again, trying to get some movement going, warms up your joints. It's very good for you, even if you do this just in isolation. So, all right. If we stand roughly shoulder width apart, we can do bear. So pretend you're kind of grabbing like a yoga ball or something like that, and we're going to shift off to one side, turn to the outside, and then shift your weight back. This is called bear, and you don't want to go too far. I was slightly admonished today because I think my hip is slightly outside of my base, maybe. But I'm getting better slowly. He seems to think I'm coming along much nicer than, I should, given other factors. And I'm like, yeah, but I've had like almost 20 years of karate, so I think I'm probably doing okay, okay. It's still slower than I want to go. My learning is slower than I want to go. But we had some fun time, and then we were doing a bit of some push hands work, and which is more of a free form like fighting. So we're getting into basically sparring a little bit with each other, and he's just like, "Look, you know, you seem you seem to be carrying a bit of tension today." I was like, "What do I have to be nervous, anxious, or you know, friggin' anything else about? What do you think?" He's just like, "Yeah, okay." But then I'm also like, and I'm slightly frustrated because you're just like tossing me around like a rag doll. And like, what the hell am I supposed to do? I weigh probably 1 to 2 stone less than he does. That's another thing. People around here are very happy to describe how heavy they are in terms of stone. I'm like, I can't do 14s in my head. He's like, I don't know, what are you, like 14, 15 stone? I'm like, dude, no. Don't do that to me. I know I'm a mathematician, but please. All right, and then we get into this and start doing ward off as we are moving with this as well. Ideally, if we're doing it right, I think he called this cloud hands, you're moving your hands in circular motions essentially the entire way, and it looks like they're moving in actual circles. This, I would say, is probably a little bit similar to some of the things that we saw in Nine Souls when we were playing Nine Souls like not too long ago. Last month? Yeah. Beginning of this month, last month. Okay. Oh, yeah, and then I went like that, and he was like, God, your hands sound like they've got actual power in it. I'm like, it's just how I learned to flick them. Okay, so we start here, V shape on the feet, and in order to do the first, again, almost to the first third of the form, feel like we're being carried by little uh, uh, string attached to the top of your head through the spine, and basically drop everything else, or at least relax everything else. It doesn't have to be dropped. We step sideways, straighten the other foot. Energy ball to the right. Oh, that's too bad. Lean in, step out, ward off left, turn. Turn on the ball of the foot here. Do ward off this side. Roll back, press, separate, push. When we come back this way, and I have to watch this because he said this is a much more gentle move than I've been giving it credit for. So we come from here, we come this way, come through. Nope. And I'm putting too much emphasis on it, I think, was the issue. Ah, there we go. So from here, all the tension is in the right inguinal crease. And basically, all I need to do is pick up my heel, and this will allow me to kind of unwind my body as well as do the single whip here. Then we come out this way. Lift hands here. retract and do a shoulder. That's a shoulder drop here, followed by coming in for crane. That needs to be further out. There we go. And then from here, last time we talked about a tiger strike, where right, left, right. This needs to come down, and this needs to come across at the same time, and while we're moving our body weight. So if I'm here, I need to go 1, 2, up, sweep, hit there. Okay, then I don't have enough room. From here, we're going to move up, even, and then put the left foot out and the hip down. These come out and around, and we do what's called strum the lute. So this is going to be a compression move here to try to bring everything in. It's also a block, but that's what we learned. Yeah, that's what we learned today. So we did strum the lute, and then the next one, I think you said the next move is also, yeah, next move is also a tiger strike here. So leg sweep knee. I don't remember exactly what that was. Then we're going to do both of those at the same time here. So if we go back to crane, we're going to go right, left, right here. Step up, strum the lute. And then, no, other one. 1, 2, nope. Damn. Yeah, it's just 1. Right, left, right. Good times. Yeah, we're doing all right. Apparently a little stressed out when I was at my Tai Chi class today, but so this is supposed to be like a public lesson that anybody who's been doing stuff with him can go to. I'm the only one who shows up like 99% of the time. So I get a private lesson for the cost of not a private lesson. I'm like, look, if you need a raise or something, we can discuss that. He's like, don't want somebody to start showing up and then you being like, oh. I'm like, dude, I'm paying for a service. And that service is well rendered. It doesn't really matter how many other people are here. Right. So we were talking about Taylor series. And for instance, if we wanted to find the value for pi using the Taylor series, we can go with a depth 4 Taylor series using 3 derivatives. And like, this is kind of nasty, but if we plug in the number 1, it's not too bad. Right, we can't plug in the number 1 until we actually have the Taylor series or the full derivative of it. But nonetheless, we're in pretty good shape here. So if we right, if we evaluate this at 1, uh-oh. cool. We might have the same value in here, at which point, is it just going to cancel out? Oh no. Okay, so using the Taylor series, we're trying to do that right there. So it is just a regular power series, a sub k times x to the k, but we're going to be doing it specifically right? It's going to be x minus x0 to the k for any non-zero starting point. Yep. Yeah, our pi is going to cancel out. Man. Harumph. I should have seen that coming. There are some math tasks, but more that math and puzzles tend to go well together just because of like mathematical thinking as a whole is just much more robust, I guess. If you just try to solve like a puzzle using kind of non-mathematical standard logic, it might work, but at the same time, if you use like mathematical thinking or problem-solving thinking, generally speaking, I've found it to be better, but it depends on the puzzle. So I have currently 2 pages here, third page here, and we're starting to get into the 4th page here of notes in terms of like what individual things are we discovering and what are the relationships between these things. And like there are some puzzles that we definitely have not activated yet. They're all over the place. You know, do I need to put certain rooms in certain places? That sort of thing. So there is something else we can do here. Right, the nice value that we have here is the inverse tangent of 1 is pi over 4. But if we try and use the inverse tangent function and then evaluate it at 1, that's going to cause some problems. If we don't evaluate it at 1, that's likely also going to cause some problems. uh, hmm. Hmm. So kind of the way that like mathematical thinking typically works is that we start looking at like all of the available clues and evidence that we have in front of us, and then we start like creating a list of priorities in terms of like what do we know and what do we need to know in order to fulfill hypotheses. So almost immediately when I started playing blueprints, I noticed the pictures on the wall. And so, like, were the pictures on the wall the same for like um, all rooms that I put in the exact same spot? So, in other words, were the pictures on the wall independent of the rooms or independent of their locations? And very quickly we found out that the two pictures that we find in most rooms are going to be the exact same in the exact same coordinate, regardless of what room is there. Unless, of course, that room just doesn't have pictures. And then I was like, well, what are these things? Like, what are in the pictures? So on one of them, there is a picture of a bat. It is clearly a bat that is above a forest and all this other stuff. And the other one is a bath, a porcelain bath. I said, that's rather interesting. They're one letter apart. Is that true for all of the other stuff we have? And so when I started looking at the pairs of pictures everywhere, there is one that is desert dunes and a ampersand. And so I looked at that and I was like, okay, that's kind of weird, but what is it? It's an ampersand and it's sand dunes. Oh, sand and. Well, those are also one letter apart. So I started keeping track of where all those letters came up on a miniature map, and then we eventually we just cracked the puzzle last night. So I know what it says. That does not necessarily mean I know what it means. All right. All right, so like no other values are going to be nice for this, really. We could put in so if this one is centered at 0, as it currently is, like through the function itself. If we center it at 0, then we can let x be 1, and it's unfortunately going to like cancel out. We could let x be 0, or x0 be 0, and we're going to get, I'm assuming, very slow moving values. No, that's even worse. Never mind. So we're going to get 0 here. Hmm. Yeah, we don't want 0 for x. Yeah. So we're trying to figure out, like, where could we put this particular function so that we can find the value for pi pretty easily. So we want something that's going to come back with nice numbers for each of these derivatives of f. So this is not coming up particularly nicely. Okay. So not inverse tangent. Um, hmm. All right, the other inverse trig functions are probably going to be the same. Because like if we do inverse cosine of x, right, then we know, for example, f of -1 is equal to pi, which is the cosine inverse of -1. If we were to do this, then we would say, okay, cosine inverse of -1 is going to be the following instead. So it's going to be k goes from 0 to infinity of a sub k times, and again, we just did this, so f kth derivative at x sub 0 over k factorial times x minus x0 to the k. So our first term here is going to be the 0th derivative of our function at the particular point. If it was -1, then we just get pi back. And then we're in the same problem we were before. If we plug in 0, then we're going to get 1. And again, the derivatives of the inverse cosine function are now going to get us really gross stuff. So it's negative square root 1 plus x squared. Yes, true. Right, and then if we want to do this, this is the problem. So now we're going to end up getting all this. No, that's okay. I was thinking backward on this one. So if we did cosine inverse of 0, that would actually get us pi over 2, which I think that's bad. Again, I think we're going to get like very slowly converging values. There is also the possibility that we don't have a radius of convergence that is compatible with nice values of the inverse cosine. Yeah, so I'm just trying to see if there's a reasonable way to do this. I think the answer is no. So this is going to be a negative 1/2 that comes down as its exponent, making this a positive 1 over 2. This is now going to be 1 plus x squared to the 3/2 on the bottom, with now a 2x on top. So that is going to get rid of those two. It's going to be, we take the derivative of the top, we get 1 over 1 plus x squared to the 3/2. And then here, this is going to be, we take down a negative 3/2 exponent. So it's going to be a minus 3x over 2 parentheses. 1 plus x squared raised to the 5/2 times the 2x we would have gotten up there also. Next question. Do we do this? Might as well. This is going to be gross. 1 plus x squared over 1 plus x squared parentheses 5/2. Okay, minus 3x squared. 1 minus 2x squared all over 1 plus x squared to the 5/2. Yeah. So just after a few terms, this gets really gross and really hard to calculate for these inverse trig functions. We probably could do something much better. Yeah, if we just have x equals 0, this is going to end up being 1, which is not going to be helpful. It would need to... Well, okay. Actually, that wouldn't be too bad because we do have a k factorial term. So... we do, in theory, have the problem with the cosine inverse. Okay, so let's try this. Cosine inverse of 1 is going to get us 0. Okay. Let's try it. So, it says that pi is going to be equal to cosine inverse of -1. Yeah. Right, f of -1 is what we've actually got up there. Yeah, it just always gets the first term to cancel out. So this is not working because I'm not thinking. Okay. Yeah, so trying to find the value for pi, kind of doing this a posteriori thing, doesn't really work too well. Where we're like, oh, I know a function value that's going to work for this. We're going to end up with f of -1, right, as our literal first term. Because it's over 0 factorial and then times x to the 0. So none of that matters. Anyway, this is not the point, right? The point of all of this is that Taylor series are awesome. And we can show like why they're so awesome by saying like, okay, we can approximate sine of 3 using Taylor series n equals 4 and x0 equals 0. It's like we could just come out of can just use a Taylor series to approximate what is the sine. What is 6? What is the sine of x? Right? Again, a sub k. No, don't do that. We know what it is. The kth derivative of x sub 0 all over k factorial multiplied by, we know f, it's just sine of, no, that's f, jeez, multiplied by x minus x0 to k. So the sine of x is going to be equal to, here we're going to take the, again, this is going to be sine x, cosine x, negative sine x, negative cosine x, and then wrap back around again. So 0th derivative, first derivative, second derivative, third derivative, and then this loops back around to fourth as well, etc. So this is just literally a cycle. Aha. If that is your plugging it into the formula and ending up getting the alternating odd harmonics, then yes, that is going to be acceptable. It's also going to be incredibly slow. All right, so then here, 0th derivative is just the sine of 0, which is just going to be 0, plus cosine at 0 over 1 factorial, right, times x minus sine at 0 times x squared all over 2 minus cosine at 0 times x cubed over 3 times 2, which is going to be 6, plus, and then go on from there. So we have this. This ends up getting us x minus x cubed on 6 plus x to the 5th on 120, so that should be 5 factorial, minus x to the 7th over 7 factorial is, what, 14? Nope, 720 times 7 is 49, 50, 40? So if we do sine of 3, this is going to be, so when I say n equals 4, I usually mean number of terms rather than like, okay, n equals 4 would end here. Like, that'd be really ridiculous. Okay, so here it's going to be 3 minus 3 cubed over 6 plus 3 to the 5th on 120 minus 3 to the 7th on 5040. I really hope that we got one that's reasonably bigger. Okay, this is going to be an approximation now. So it's no longer actually going to be precise. So 3 minus, let's see. If we take a 3 out of each of those, it's going to be a 9 over 2. 3 minus 9 over 2 plus. Take a 5 out of 120, you're left with 24. Oops, not a 5. Nope. We need to take a 3 out. It's going to be 3 to the 4th is 81 over 40. This is not going well. I think the major reason that this is not going well is that it's so far away from 3 that it's gonna just be ugly. On the other hand, if we let this be sine of x minus x0 should be a nice number. So let's do pi. because all of our sines are still 0. We're only going to get different stuff on cosines, which means opposite signs of what we have here. So we get a negative x plus x cubed minus x to the 5th plus x to the 7th. But nothing else changes. That's a lie. Okay, our x's change, because it's not going to be x anymore. It's going to be x minus pi. To the 7th, to the 5th, to the 3rd, okay, so negative parentheses 3 minus pi. So pi minus 3. Plus 3 minus pi to the 3rd all over 6 minus 3 minus pi to the 5th over 120. This is also a small number now. So 3 minus pi is 0.14159. Well, I mean, like, I could find a faster method by just using the Ramanujan one. But, like, we're just trying to say, like, how would you do this if you're just doing, like, a random project and you need to work on, you know, something. You need to have some sort of value for it. This would be one way to do it. And not terribly difficult. It is a little time consuming without directly plugging it into a calculator, which naturally everybody's going to be doing in this world, right? Because we could plug it into Python or what have you. I was getting secondhand grief today from, I believe it was Autumn FNAF of the Breaking Math podcast, because she was like, why would you use Python for math stuff? Granted, the co-host agreed, and he was like, yes, you should use C or Fortran. That's about it. All right, see you in 3 minutes. We got an ad break, and yeah, we'll be right back. Thanks for coming, everybody. Alrighty. Right. So, usually not pretty, but be worth something. Got to keep that fitness up. 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15, 17, 18, 19, 20. 1, 2, 3. Good enough. Okay, so I did find that when I plugged this stuff in, this term, oops, right, naturally enough, is going to be a positive 0.1415926, etc. Of course it is, right? It's the difference between 3 and pi. And then the next term is a negative 0.00047311,957. Now there's obviously more numbers after that, but that's what we got. Next one is going to be a positive. And that's going to be a negative p over 2 to the 5th over 120. 0.1235647426664. More stuff after that. And then this is going to be a minus. Why is this bore? How's it going? This last one here, right, is going to be a minus. It's p to the 7th over 5040. Gets us a 2.26388 times 10 to the negative 10th power. We're doing all right here. How's things on your end? So you can see that even with just 4 terms, this converges real fast. If we can find a value that is reasonably close to the target value that gets us a nice number, then we should be able to come up with something that's, like, again, pretty reasonable. The issue with trying to find the value for pi, right, we saw earlier there are kind of 2 reasons, or 2 issues that exist. One is that we don't really have any, like, nice values that are pretty close to pi for, like, any of these particular functions. 101 on your slope test, awesome. Well, thank you very much. And I'm very happy that you were able to put the work in and get it figured out once I unlocked whatever thing might have been a key understanding. right. So if we just want like Taylor series of particular functions, we can also do that. I know there were several that like right, if we just want to look at like what is the Taylor series for sine of x, then we're doing the like what we just said before, only right, this is going to be sine of x, we're taking the, again, kth derivative of this thing. That's a terrible place to put it. dk dxk. Terrible idea, but it'll work. Over k factorial. K goes from 0 to infinity times, now this is going to be the sine of 0 is going to be our center. And then here, this is going to be x to the k. So in the first case, right, we have no derivative. So the 0th derivative is going to get us the sine of 0 over 0 factorial plus x to the k, which is 0. Oops, no, times. Jeez, where did I get plus from? That was a terrible idea. Right, take the first derivative of sine, and we end up with a cosine of 0 over 1 factorial, because that's the first derivative, times x to the first. Plus, derivative of cosine is a negative sine of 0 over second derivative, so 2 factorial, times x squared, plus, and we'll do one more, negative cosine of 0 over 3 factorial times x to the third, plus dot dot dot. So for the sine function, we end up with a sine of 0 is 0. So all of these terms, every other term, literally as far as you want to go, are all going to be just 0. So we end up with only odd numbered terms. Cosine of 0 is 1 over 1 factorial times x. Next one is minus. Cosine of 0 is also 1 over 3 factorial x to the third. And plus, we're going to get the same pattern going. So 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh. If you don't believe me, you can always go in and check yourself. Take the derivatives of the sine function. You'll notice that they'll always end up with these particular patterns. And then since we're plugging in 0 for all these, they're just 1. Makes it much easier. All right, and then plus dot dot dot. So this is our sine function rendered as a Taylor polynomial. If you'd like to see it in a short form, then we have something that looks like this. We have just 1 over, and if you want, we can rework this so that we have an alternating sign. So a negative 1 raised to the, let's see, 2k. No, because that would always be even. Raised to the, raised to the k we start from 0. Right, k equals 0 to infinity. We start with 0, so then we get a positive number for our 0th term, or the first one that's visible here. And then this is going to be over parentheses 2k plus 1 factorial. We only have odd numbers. Odd numbers are rendered as 2k plus 1, where k is any integer. So if we plug in 0, like we will for the first term here, then we end up with that one. Then we end up with 2k becomes 0 plus 1 factorial is 1 factorial. And then again, here we have x to the 2k plus 1. So it's going to have to match the same number as what's in the factorial, and also it ends up only being odd numbers. If we want, we can also like shrink this down a bit and put it up here. Could also leave it down in front because it is an x term, right? So our variable terms can go next to our coefficient terms, or they can be just kind of incorporated into one big thing. It's okay. All right. And it isn't just these types of functions. We can also have like e to the x, which is going to be, again, the kth derivative with respect to x, k times, of e to the x. Right? Hopefully I don't have to spell that one out for anybody who has already taken calculus. If you haven't taken calculus, don't worry, I'm not glaring at you. You're fine. Okay, over, again, k factorial times, again, x to the k. So on this particular case, this is going to end up being, oh, whoops, e to the 0. You know what? We can't do that quite yet. Okay, e to the... It's not e to the k. It's e to the x, or rather x0. No. E to the x evaluated. There we go. x0 equals 0. Okay, same thing with the sine function. We can't really do that. We've got to say x and then say that x is going to be equal to 0 in this particular case. Or x0 equals 0. Okay, so e to the x is always e to the x, no matter how many derivatives you take. So, awesome. The slope of e to the x is itself e to the x. Right, and that's one of the reasons that e to the x was found in the first place, was that people were aiming for, hey, what exponential function is its own slope? Because they already knew that it was that they were getting exponential functions of the same base as derivatives of exponential functions. But there was always a scale factor. So they were like, I don't understand what the scale factor is doing here. It's just weird. And then finally, when they figured out what the scale factor was, it was the natural log of whatever base you're in. So this was how logs got invented in the first place. So there was no notation for it or anything like that. It wasn't until much later that people started coming up with a notation and being able to plug it in and do all their algebraic work. Just a reminder, right? Like, new mathematics is still being made every single day. It's just a bit more complicated now. Right, this is always e to the 0. over 0 factorial times x to the 0. Okay, and then plus e to the 0 over 1 factorial times x to the first plus e to the 0 over 2 factorial times e to the second plus dot dot dot. So this ends up becoming 1 x to the 0. So 1 plus e to the 0 over 1 is 1 plus, times x to the first. So just x plus e to the 0 is 1 over 2 factorial is 2. We'll leave it as 2 factorial. That's all right. Times x squared plus. Right, this is going to continue. So the next term is also going to be a factorial, 1 over 3 factorial, times x to the third plus, and that goes from there, dot, dot, dot. Just a reminder, if anybody does have any questions, let me know. And anybody who's new here, hi, my name is Obi-Wan Pez. This is N-Simplex Pachinko. We're doing Calc 2 type stuff right now, but if you would like to talk about any other types of mathematics, feel free and place that in the chat, and we'll talk about it. See what we can do for you. Can't take me anywhere. Sorry. Right, so as a summation, this is now going to be sum as k goes from 1 to infinity of, no, 0, sorry, 0 to infinity of x to the k over k factorial. And that is it. I never actually said this one. Right, the sine of 3, which again is pretty close to the sine of pi, which is 0, ended up getting us 0.141120081. I don't actually know if that last term is rounded or if there's more stuff going on, but either way, we're at a minus 2.26 times 10 to the negative 10th power. I'm pretty confident with this number that, like, the sine of 3 probably won't even change at the last decimal place here if we were to add on a new term. nice. Said also, if you were to do something like find the square root of e, as an approximation. So this would actually be almost trivial to do with the Taylor polynomial, because here what we do is we say, okay, well, square root of e is the same as e to the 1/2. And we already have a function that is e to the x. So here, this is just saying, okay, use a Taylor polynomial. E to the 1/2 is going to be equal to 1 plus a half plus a half squared over 2 factorial plus 1/2 cubed over 3 factorial plus dot dot dot. Okay, and if we go to a certain number of decimal places, right? Let's find out how many decimal places, or let's find out how many terms it will take to get my calculator to not be able to tell the difference anymore. So here, 0.5 store into, all right, sure, x. If we want e, that's not it. E to the x, this is going to be 1.64872171. This is going to be equal to, the first two terms are just 3/2, plus. Next term is going to be 1/4 divided by 2 factorial is 2, so this is going to be 1/8. Plus, a half cubed is 1/8 divided by 3 factorial is 6, so this is 1/48. Both of those together are that one. Right, so this is going to be 1.5, then also right, so these, as they stand right now, again, as they stand right now, this is going to be 1.64583 repeated. So not very good, but that's only 4 decimal or 4 terms that we're using out of this. So again, how long do we have to go in order for it to stop making a difference between these two? It's actually something that I think I coded up on Python at one point, but I don't know where it went. It's essentially trivial to actually code this. All we really need to do is find the new term give it a second. Any second now. Good evening and welcome to everybody from Penn Center's channel. My name is Obi-Wan Pez. This is N Simplex Pachinko, and we are doing mathy type stuff tonight. Talking about Taylor's series as discussed in Cracking the GRE math subject test from Princeton Review 2nd edition, copyright 2002. It may be a 24-year-old book, but let me tell you, that math has not changed very much. Hope y'all are having a great, what is it, Wednesday? Yeah, Wednesday night, afternoon, I guess, in some places. And those of you who are in Europe, have a good night. Let's see. So we were just talking about Taylor polynomials and how to first create the Taylor polynomial for any particular function, and then also be able to use it to find a particular value that we want. So for instance, find the square root of e. In the calculator, we can just get that, yeah, sure, it's 1.6487212771. But by hand, right, if we're using a Taylor polynomial, how many terms will we need before this stops being any different? So the way that I would do it is we're going to calculate individual term by individual term, iterate through the index k for what term we're on, calculate the new term, add it to the total that we have so far, then find the difference between that and like the actual value, because yes, if you know the actual value, it's not a big deal. If you don't know the actual value, you can compare it to itself. So we want to know when it's going to stop changing by the tolerance of that particular term or that particular calculation method. So here, if you can get any of these numbers out to like 1,000 decimal places, and your computer will do it without really taking over almost at all. Might get a little dicey toward the end because you're raising something to 1,000th power. But essentially what I would do is I'd say, okay, here's the difference between this term and the one we just had, like the total now versus the total that we just had. Or calculate the current addend, right? The number that we're adding to our total. If that number that we just calculated is like less than 1 times 10 to the negative 15th, like who cares? We can stop. That is not going to add up to a significant amount within any sort of reasonable amount of time. So, with what we got here, we're trying to figure out, like, by hand, i.e. we're just using a standard TI, how many terms do we need to go before this is going to become identical in the TI operating system? So with this being 9 decimal places, right? We'll just keep going with this. This is going to be x to the 4th over 4 factorial is going to be 24. X to the 5th over 120. Oops. Plus x to the 6th over 720. Yeah, we're still oscillating, so like... Actually, it's not even oscillating. It's just straight adding numbers to it. All right, x to the 7th over 5040. We're getting real close there. Plus x to the 8th over 8 times that is going to be 40,320. All right, one more. 9 times this is going to be 362,880. Ugh. 362. 880. I think that's right. Yeah, we're real close. 10. That one's an easy one. I just add a 0. Right, and then we want E2.5. There we go. Okay, so it took 10 terms because this one converges a little bit slowly. Now I'm wondering if I broke something. Oh well. Anyway. Anybody have any questions on any types of mathy type things? So, not just Calc 2, but feel free if you have any questions on various things. My ability ends at about the sophomore-ish level of community college or sophomore-ish level of a public 4-year. We're talking like multivariate differential equations and linear algebra. I can do a little bit beyond that, but I can't guarantee my work. But I have taught differential equations a number of times. It's very fun. If anybody else is interested in other stuff we do around here, oh, right. If anyone does not yet know any of our other awesome mathy type streamers, here's a list. We have Slim from the Academy of Useless Ideas, Dr. Gold from Actual Education, Don Factorial, E.N. Stuckey, E to the 2i Pi, that's Zach, Merriweather Remark, Penn Center, who just rated in, Phobostream, Physics and Depression, Tellus Teaches, and the Tutor Wizard. And over in our Friends of Math group, we have the study groups. So If you're also interested in learning cool stuff, you can talk with any of these people. So Rendeo, Math Spellbook, Fizzbuzz, Suna Owl, and Walking Stick Library. They are off learning cool stuff and think that you should too because learning is awesome. And if you have any other perspectives of all of the, if you have perspectives on any particular thing, whether you are a student or a teacher of a particular subject, all of us are rather interested in like learning about it. So, hey, Pan. I didn't hear something. I didn't hear your walk-on go off. That's a little weird. I didn't turn it off. No, it's right there. Mine went off at the beginning. Okay. Okay. No, never mind. Anyway, um, and also on this channel, we do on Tuesdays. We just completed our second, third. There it is. Hey Zach, how's it going? Blast in my ears. All right, let's go back over here. And where is the my library? My stream? Hmm. That's not it at all. Okay, well, anyway. Nah. I that's footsteps. Weird. Anyway. For some reason, pens didn't go off. Anyway, I have also just for the night taken off um, all of the desktop audio for uh, for Twitch Twitch VODs. So those of you who are here on Twitch or I suppose on YouTube eventually will notice that now there is no more music. So I sort of fixed it. It hasn't entirely fixed it. I need to break apart the two sources and then be able to uh, be able to send all of my music through a separate browser source or whatever you all do, audio source. It was just not playing nice. And so I was like, all right, fine. We're just gonna knock it all out right now, and that way I will not get alerts over and over and over that a bunch of my audio has been muted. Like now it's just none of it's gonna get muted. So, aha. And like I said, I was rather disappointed to find out that the company called No Copyright Sounds is apparently in some sort of dispute talk with some company that keeps claiming copyright on people's YouTube channels. So, No Copyright Sounds, I believe, is not very happy at the moment and issued a court order that, like, their, I guess, distribution company or something is not going to be able to. I have not read the entire injunction. It's not even an injunction. It's a like preliminary court case document. So they're getting into it with a couple of companies right now. And admittedly, I don't speak legalese, so I won't be able to parse truly what the court case is about. Hmm. Anybody who was here yesterday, my neighbor, you know this story, so sorry. My neighbor made some bread, and he was telling me that he was making bread and made an extra loaf for us. I was like, oh, that's so nice. But it was ostensibly in exchange for, like, mailing a letter through the U.S. system to some of their friends in the U.S. system. Turns out that they are in an FPO in Japan, and so, like, we can send it through the APO here. And when my spouse got to the counter, she was just like, I don't know how much this is going to be, but, like, can I have a receipt? Lady looks at it and she's like, give me a sec. Punches it up on the computer, like, nah, it's free. And tosses it in the thing. Like, all right, cool. So we got free bread for doing a very minor favor. We're just getting down to the last couple of pieces. Oh. Okay. I will actually finish my sentence this time. So on Tuesdays we're doing blueprints, which is currently we just finished our third stream of blueprints. We have finished day 10, I believe, in game. I just got onto my fourth page of notes. And yeah, Penn, I didn't go too much further beyond what you saw last night, I think. And also, hello and thank you to all you who are watching the VODs as well. Um, I have seen a massive uptick in recent months, or compared to any of the recent months. So I'm not exactly sure what happened, but thank you so much, everybody. Um, I need to get all of this stuff put onto YouTube. Um, I'm currently working on January. No, I'm currently working on, yeah, December. Okay. So I believe I've gotten almost all of November done, and we're starting to get into December on a lot of stuff. Like I said, thank you so much for coming. Thank you so much for being here and hanging out, spending time, all that good stuff. Uh, I never expect anybody to like sub or gift bits or anything like that to this channel because, quite frankly, we're an educational channel. This is not where we're about. But, you know, if you are one of those people who has the ability, then awesome. Um, it is going to be my goal at some point in the next, year and a half while we're still here, to need to pay His Majesty's taxes. So, so maybe that'll happen. We'll see. But so far, I made, I don't know, it was like less than $200 last year. And so it was like, I asked a lawyer and they're just like, it's not worth the paperwork. Just, uh, I'm like, all right, well, I hope you all have a good evening. I think we're probably going to call it here unless anybody has any, like, in, you know, any questions about cool stuff. Um, 500 over the course of 2 years. Yeah. Like, I filled out the EZ form when I was a teenager, right? Because the 1040 EZ, I made $700 over the course of a summer. And so it's like, excuse me. Cool times. Okay. I'm not seeing anybody else on doing educational stuff at the moment. Oh, there we go. Finally made it to the bottom. Danny Anduza is on talking about the world's largest turtle, the leatherback. So I think we will go and see Dr. Danny Anduza over at Paleontologizing. And I will be back on Friday for more Against the Storm. I am also currently on a deep space expedition in Elite Dangerous. We're currently doing what's called Distant Worlds 3. I am, goodness, thousands of light years away from where I have been spending most of my time. So it's fascinating just being in a completely different area. We're doing uh, both planetary and star scanning in order to like just map places that nobody's ever been before. So we jumped into an area and I like took off from the carrier and just opened the map and it was just stars, like hardly any space in between. And so it was like, all right, well, I'm gonna spend the next hour or two, I guess, figuring out what stars we're gonna go to. And like I hit probably about 20 to 30 stars and went down to a found all of the planets in like a fairly small system and got first footfall. So like I have the first footfall on these planets in the middle of nowhere and first mapping of almost every single one of those systems. It was really cool. So become your own business. Yes. So I'm intending to register as an LLC at some point. I just, I need to I need to make enough money that even the paperwork is justified. It's very sad. Anyway, we'll talk about more of that stuff later on Discord. So, thank you so much, everybody. My name is Obi-Wan Pez. This is N. Pachenko. Let's go see Danny Anduza at Paleontology.